Ho ho ho, ladies and gentlemen. So in today's video, we are going to continue our discussion with acids and bases. And I told you in the last one that we're going to be focused on something called Pka and pH. This is our next topic that we need to address before we go further into this organic class. So pH you probably feel okay with. This is something that's taught very early on in elementary school. What is an acid? What is a base? Based on the pH values of those solutions. It's typically the very first time that you get acquainted with pH levels. So pH we are going to mention, we are going to talk about them, but I want to put a focus on this one. This is pKa. And this term should have been introduced in a general chemistry class. Chemistry 152, if you took that at Cape Fear. Depending on your instructor, depending on how long they took on this material, you could come away with a very strong understanding of pKa or a very weak one. So it's my job to pretend like you have never seen pKa before, and to introduce it just like I would in a 152 class, and then talk about it in that form and fashion. So we're going very basic here, okay? So once more, I'm going to treat it like you've never seen it before, and we're going to talk about the basic definition and what it does and the meaning behind it. The reason I'm going to do that is because very often there's a big question that concerns pKa. A lot of people feel uncomfortable with pKa. They don't really know what it means. They don't know what it stands for. They don't know how it relates to acids and bases. But it's a very easy concept. And I think that you'll see that when we begin to do some of our examples and some of our lecture talks with it. So pull up beside me, nice cozy fire, maybe roasting some marshmallows, and we'll have a grand old story about good old pKa and pH. So here we go. In the acid and base world, we have two categories. One is strong and one is weak. Now, I'm going to talk about this in terms of acid, but you need to understand that bases are strong and weak as well. But I'm going to only focus on acid because the same description goes for both, okay? Now, as far as strong acids go, what this means is that it actually gives up all of the proton that the molecule can. That is the definition of a strong acid. So for instance, HCl is hydrochloric acid. HCl is a strong acid by definition. What that means is that that acid will give off all of the proton that it can. It will not keep any of it behind. It is not greedy. Imagine someone that just got a paycheck and they go on a shopping spree and they spend every dollar that they just made that day on that check. You might know some people like that, and I hope that you're not one of those people, but you could at least know some of those people. Don't be a strong acid. Don't be spending everything that you have all in one day. You never know when you'll need it. So this is the attitude that those strong acids have, though, and this is just how they operate. This is how they do things. And quite honestly, there's really only about 7 strong acids that we ever need to talk about in a laboratory environment. That's it, folks, just 7. Out of all of the acids that's out there, 7 of them. So they're not very many at all. Now, on the other hand, weak acids or weak bases. Again, I'm only going to address it in terms of an acid, but these do not, of course, give off everything. That's not what they do. They do not give off everything that they have. So if I have an acid, and let's say that this acid is maybe HCOOH. There is a proton here, and that proton's written in front, so triggering acid, acid, acid. But this formic acid is what it's called, is not a strong acid. It is a weak. What that means is that it will give off some of that hydrogen. So when it gets its paycheck, it's going to spend some of that money that day, but it's not going to spend all of it. It's going to keep some of it behind, and it's going to keep that amount behind until it actually needs to use it on a rainy day. That's the difference between a strong acid and a weak acid. It's also really the difference between a strong base and a weak base, except instead of giving off hydrogens and so forth, we're talking about accepting hydrogens or accepting only some of the hydrogens. That is how that definition changes. But folks, that's all there is to it. Weak and strong basically refer in the field of acid how willing it is to give off the protons that it has. Now, I told you there's really only 7 in total. And here are some examples of those strong acids and those strong bases, but they're only going to be listing 6 of each for you, and that's about it. The reason they did 6, they did the top 6 that were the most common, and they kept this table pretty even, so they gave you 6 acids and they gave you 6 bases, but there's actually a few more in each category on both sides, but these by far are going to be the most common. So 6 strong acids, if you look here, perchloric acid, HClO4, HCl is hydrochloric acid, HBr is hydrobromic acid, HI is hydroiodic acid, HNO3 is nitric acid, and H2SO4 is sulfuric acid. All of these are strong, which means they all give off every proton that they can. Over here on the right-hand side, these are 6 strong bases, which means that they will accept protons whenever they can, and they will accept as many as possible. They are not going to reserve their sites for anything else. If they see one, they're going to take it. So lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, barium hydroxide. Those are the 6 strong bases that we need to be aware of. Now, if you look at the positions of the periodic table, you're going to see chlorine, bromine, iodine, all in the halogen group, but they're going to leave off fluorine up here at the very top. It is not classified as a strong acid. And then you look at nitric and sulfuric, N and S. You're actually over in this area right now. So they're all kind of clustering into the same spot, which is a good sign because the periodic table is periodic trends. And if these trending strong acids, then we will find quite a bit of strong acids in that area. And we do. So that makes us happy. It's another confirmation that the table is structured the way that it is in a certain way. And it's the proper way that we've done it. 6 strong bases, you look at those locations, a lot of those are the alkali metals and the alkaline earth metals in the first 2 columns. So again, they are very close and they are clustered together in that section, and that makes us very happy because another periodic trend has been satisfied onto the table. Well, these are only a few acids and a few bases that we're going to see. And the textbook will give you a chart that might look something similar to this. If it doesn't look exactly like this, it will look something close. And what they've done is that they have organized this chart in terms of acid on the left and in terms of base on the right. And they have ranked them for you. Okay, so the reason that I'm saying ranking is because up here at the very top, we are seeing our strong acids, perchloric, sulfuric, HI, HBr, HCl, HNO3. All of these we said were very, very strong. And they're listing them up here at the top of the chart. So this is in ranking order, folks. That's how I look at this. And then below this line, this hydronium ion, we start to venture into more of the weaker acids that we might see in a laboratory. And these are things like carbonic acid that might be in your soda. This is acetic acid, which is the vinegar bottle that might be in your pantry. We go on down. Ethanol is listed, which is what you find at the ABC store. Ammonia is listed here at the very bottom, which is a general cleaning agent that you can find at the dollar store. I mean, all of these are part of the acid-base world, but they are very, very weak, meaning they do give off the hydrogens because they do have them, right? They are present. Look at there. They're right there in front for the most part, all the way down. But they're not going to leave them all at once. They're going to keep a hold of some of them, and they're going to grab onto those for another rainy day. And that is the definition of a weak. Over here to the right-hand side, they're doing the same thing. But if you look at the way this is organized, it says over here, increasing base strength. And it looks like our strongest bases are down here at the bottom, and they get weaker and weaker and weaker as we go up. All right, so this goes back to the whole conception that a strong acid makes a weak base. And that's why this table is organized the way that it is. So perchloric acid is a very strong acid, which means it gives off the proton that it needs to give off, and that's ClO4 minus. Okay? Once that ClO4 minus happens, this is extremely weak at this point, meaning that it doesn't want to take the proton on again. Because if it does, it's going to revert back to this acid, and we already know that that acid will kick it right back off if it does it. So this is a very weak base. It's not going to go around and waste its time trying to find a proton to take on when it knows that once it gets one, it's just going to spit it back off again, because perchloric acid doesn't like to stick together. It doesn't like to keep that proton. So strong acids make weak bases, and vice versa. Strong bases make weak acids. So the relationship here is going to be opposite, and that's what you're seeing on the chart that's in front of you right now. So another example, down here at the bottom, this is the method ion. This is extremely basic. It is very, very strong. So it's going to gather a proton whenever it can. And when it does that, it makes the CH4 molecule. Well, because this is strong, and because it's actively searching for proton every single time, when it does get one, that CH4, if it tries to spit it back off and it reverts back and makes CH3, CH3 will just slap it back on there again. So this is a very weak acid because of that. It is not going to be a proton donor. If it was a proton donor, it's going to be one for split seconds before CH3 minus decides to slap another proton back on it and call it a day. And that day is CH4. So this is the relationship between acids and bases as far as strength is concerned. Now, we've already seen equations, and we've seen us going through examples of labeling things as acids and labeling things as bases, right? So over here to the left-hand side and over here to the right-hand side, this HCl and Cl, these are the two counterparts right here. In a previous example, we said, listen, HCl goes to Cl. It lost a proton. The definition of losing a proton is an acid. And this makes a conjugate base. They left the word conjugate off here for you, but it's a conjugate base. They wanted you to focus on the word base, though. That is what we're doing. All right, so here's water, and if I compare that, here's water, and after the fact, we got H3O, not H2O, so we've gained a proton. All right, so if I go through water, and I look at what's happened here, we've gained a proton, so by definition, it is a base. Over here on the other side, if that is a base, this is going to be listed as a conjugate acid. They leave the word conjugate off, though, because once more, they want you to focus on the word acid and the word base. The other thing I want you to take a look at is here with the arrows. This basically represents equilibrium. Equilibrium means it will go back and forth, back and forth, back and forth, back and forth. Okay? There's no stopping it. HCl and water make Cl minus and H3O plus, and then that does react together again to reform HCl and water, and this goes full circle, over and over and over and over. Okay? So, if this happens though, that's okay, not a big deal, but there's going to be a side that is preferred. There's going to be a side of this equation that these reagents like the best. And that is always drawn with the longest arrow that you see, in this case, up here at the very top. That longest arrow is letting you know that the most preferred method is over here on this side. So if this reaction goes forward, it does go forward. It does create chlorine. It does create H3O plus or hydronium. This is where this reaction prefers to stay, but at the same time, it can revert back on itself. It can remake the reagents over here to the left, and then those reagents can react one more time and go over to the right. And we get the full circle that goes over and over every single time. Down here at the bottom, it's just another example. Here we have NH3. The NH3 goes to NH4. So this has gained a proton. It's accepted one. So therefore, this is a base, and that makes this a conjugate acid. So they're just going to label it as an acid over here. Here we have water, H2O, and then over here, we see the loss of a proton. The loss of a proton means that this molecule, H2O, is behaving as an acid, and its counterpart is a conjugate base, but we're only going to call it a base. All right, so just like above, this reaction goes forward, reverts, forward, reverts, forward, reverts. There's equilibrium. Which side does this prefer? Well, this arrow tells us. That arrow means that all of these are going to be the preferred reagents. So if this equation does flip-flop back and forth as much as it can, over here to the left-hand side, those reagents will be preferred and they will show up most of the time. So we do get a little bit of product, but those products, if they get formed, revert pretty quickly and they give us ammonia and water all over again. So this is really the first concept of equilibrium that you should have been taught in general chemistry. We have acid-base theory going on. They react together. They react and quite honestly give us other acids and bases. And then we have a preferred side of the equation that they will prefer. And all of this is driven due to strength. How strong is the acid or how strong is the base? That is what all of this boils down to, folks. So remember, I told you that we have a chart that gives you strength of acids. And we also have another chart that gives us 7 super strong acids and bases here. I mean, those are so strong they will beat anybody up on those charts. And we're going to have to be able to use these charts in order to determine which side of these equations the reaction prefers. Because that's going to be the number one question that they're going to ask from this section. If you have this reaction, and here are your reactants and your products, which side does this equation prefer to stay on? The left-hand side or the right-hand side? And the way that we answer those is looking at the strength of the acids or bases that are involved. So with that said, that's what we're going to discuss in the next video. I've already rambled on for 20 minutes on what an acid and a base is and flip-flopping reactions back and forth, and that's okay because again, you might need it to hear that information. And that could have been new information for you. So I know that I didn't waste my time. And I know that I didn't. So in the next video, we'll pick up from here and we'll talk about more equilibrium and we'll talk about strength, and that will lead us into what we call pKa.